My name is Philippe Lalanne, and I will present an introduction to the software MAN for modal analysis of nanoresonators. And more detail, of course, can be found into a recent archive paper. With this slide, I would like to have a rapid overview of the software. I would say the software is 10 years old, basically, has been launched in 2013 for the first time, but we are able to collect the statistics for the downloads only since 2 years. It comprises tutorials with many examples. Basically, we are able to deal with any material, dielectric, metal, even non-reciprocal material. We are also able to deal with any geometry, photonic crystal cavities, Mie resonator, plasmonic antennas or gratings, photonic crystal. Since version 8, the MAN software comprises two solvers for the sake of generalities. We have also included many toolboxes like QNM toolbox on multipoles, on nonlinear optics. They will be introduced rapidly in my talk. And also for complicated geometry, the software is backed to COMSOL. And we have included something like 20 models that can be easily changed to accommodate for the geometry that the user would like to use. I would like to emphasize that the solver QNM pole can be basically used with any frequency domain Maxwell solver. The software which is especially backed with COMSOL is QNM egg. Before describing the software, let me first introduce a few review articles published by our group over the past few years. The first article here on the light interaction with photonic and plasmonic resonance is the main and the first review written on the topic. We have recently written a second perspective article in ACS, where basically we more emphasize the physics of quasi-normal modes. And this year we published a report, an in-depth report on, let's say, the maths, the fundamentals, if I could say, the mathematics of the quasi-normal mode, where we emphasize normalization issues, orthogonality, and completeness for the case of electromagnetism, of course. The software applies as well to radio frequency of optical component, but I would say that more generally the techniques or ideas which are developed in MAN should be transposable to other type of wave. I mean, I'm thinking especially of acoustical wave, acoustic resonator, mechanical resonators. In the group, we have been working extensively on resonator for nanophotonics, and basically we have studied with the software MAN all the resonators that you can see on this slide, from the, let's say, ultra IQ resonators in microspheres to photonic crystal, plasmonic, nano gap cavity, and even recently we have been working on pico cavities. Before providing a description of the main toolbox, I mean, let me start with an overview in which I'm going to define what are the quasi-normal modes, how you can compute them, and how you can normalize them. So I would say the quasi-normal mode are the natural resonance of any linear system. They have a complex eigenfrequency, as you can see there, and the imaginary part is related to the model of time, lifetime. And I would like to insist on the fact that in spite of the fact that they are they have a complex frequency and that the physicist is used to think in terms of real frequency, in fact, they are really observable. Here I took this image from the web. That's an acoustic resonator in that case because it's easier to measure. And so it's an Helmholtz resonator and the field is measured at some position in space outside the resonator, if I could say. And you knock the resonator at time t equal to 0. You have an initial transient, which is quite complicated. I will document that later on. But then after a while, what you see here, the acoustic signal as a function of time, is the fundamental quasi-normal mode, if I could say, of which is leaking away and in time, and so the signal is almost monochromatic here, as you see, with an exponential decay. Let us move now to the quasi-normal mode computation. I would say that mathematically they are obtained as a solution of the source-free Maxwell equation, and this solution, of course, because you have leakage or absorption loss, requires to have a complex frequency. You have also to satisfy the outgoing wave condition. That's important. So this is the maths which are related to electromagnetic resonators. Let me start by the simplest case where the material of the resonator are non-dispersive. In that case, epsilon here or mu, I didn't put any mu for simplification, are not dependent on omega. And then what you are facing is a linear eigen problem, like for photonic crystal band diagram computation, for instance. And the quasi-normal mode are the eigenvectors, and the eigenvalue are the frequencies. So what you can do is you can discretize the operator, for instance, with finite element. To satisfy the outgoing wave condition, you may use classical PMLs. So it means that the computation is quite classical. And then you compute the eigenvector and the eigenfrequency as the eigenstate, I would say, eigenvectors of this problem. And most commercial software have frequency domain mode solver and do it for you. This is, for instance, the case of COMSOL. Now assume the general case of a dispersive material. So in that case, of course, the permittivity is depending on the frequency. So first, how to define the permittivity at a complex frequency? The answer is that you have to provide an analytical formula for that. Here I give you some solution taken from that paper here, where you see that over a broad spectral range, ultra broad spectral range. People were looking at the Casimir force in that paper. You see that you basically, and this is coming from quantum mechanics, by the way, it means that you can fit with a high accuracy the permittivity, in that case recorded, let's say, from measurement and in the Palik book with Drude model plus many, in that case, 6 Lorentzian resonance. This formula just tells you that the permittivity is due to the resonance of matter and to free electrons. Now we know how to write the permittivity as a function of a complex frequency. The second point is that now you face a nonlinear eigenvalue problem. Nonlinear eigenvalue problems are a little bit more tricky than linear ones, and I would like to now present how do we solve this issue in MAN. MAN, in fact, implement two solvers for this dispersive case. The first one is QNM Pol, which has been launched in 2013. This is the oldest. This is our initial version of MAN. And the second one is QNM Ake and has been launched in 2018. This one here is relying in COMSOL in MAN. But this one here is very general, as I will comment on, and can be used with any frequency domain solver. Let us start with the first solver, QNM Pol. So how does it work? So you have to start with an initial value in the complex plane, omega 1 in that case, and then the algorithm proposes you to recursively compute new eigenvalues at complex frequency that approach actually the pole of the complex plane. And at the same time, when you perform this calculation, and this is what is very nice in this software or in this algorithm, that iteratively you normalized correctly the quasi-normal mode. Here you see that as an iteration process. Here, basically, you stabilize the field intensity, implying that you have normalized correctly the quasi-normal mode. The strengths of the solver is that it is very general. QNM pole can be interfaced with any frequency domain Maxwell solver. It's also very simple. What just need to solve Maxwell equation for a driving dipole source? You need to solve it at a complex frequency. Not all solver can do that, but we provide a trick to do that, even if you have only a solver which is restricted to real frequency simulations. The only drawback as I can see is that you need an initial guess value of the mode. So it means that, in fact, on total, I mean, this solver, QNM pole, is excellent to compute a few dominant modes only. It cannot allow you for a systematic exploration of the complex frequency plane. Let us move now to QNM EIG. So we start again from the nonlinear eigenvalue problem. And what is done in QNM EIG that this nonlinear eigenvalue problem is linearized. And it's linearized for different kinds of permittivity distribution, like the Drude or the Lorentzian resonance distribution that we wrote here. And this linearization is based on a method which is well known, which is called the auxiliary field method. I quote here in electromagnetism, right, the 3 papers. And then the result of this linearization that you have an augmented space, which is quite physical, by the way, because you see that the new variable that we introduce are the polarization and the current. So they're physical quantity. And in this augmented space, where you have E, H, P, and J, right, then the eigenvalue become linear. And then you can solve it as a standard linear eigenvalue problem. You have very efficient algorithm for that. What are the strengths of the method? But the first strength is that the maths of a linear eigen problem are quite straightforward if I compare it to the nonlinear case. For instance, we have theorem which govern the completeness. And I would say that with current eigensolver, many QNMs are straightforwardly computed. In fact, you have available software which are extremely efficient for the computation of linear eigenvalue problem. The drawback, if I could say, that the implementation of the new eigenvalue problem requires additional skills. For instance, with COMSOL, you need to know how to use a weak form formulation, but in fact, the software explained that with care. QNM pole and QNM EIG have been applied to many different situations, like plasmonic nanocavities. Here, the case of a metallic nanoparticle onto a metal substrate. We also consider a silicon nanoparticle onto a metal substrate, and by using silicon dispersion, which is quite challenging. We have also photonic crystal cavities. We use also gratings, and also plasmonic crystal, where we compute the band diagram, for instance. We have a list of available models, can be found in the repertory of available model of QNM EIG and QNM pole. There are something like 20 COMSOL models which are available. Let me move on now to the normalization. And first, let me say that normalization is essential in quasi-normal mode theory for 2 reasons mainly. First, it allows for a straightforward intercomparison of the mode strengths of various resonators. I'm talking about the mode volume, for instance, here. And here you see that in this picture, we simply compare very straightforwardly because of the normalization, the field strengths seen by, let's say, a dipole source, an atom, a molecule, for a photonic crystal cavity or for a pico cavity. And all these numbers are significant and can be compared. The second important point is that this normalization allows you for an analytical expression of the quasi-normal mode excitation coefficients. There is a tricky point in relation with quasi-normal mode normalization. It's the fact that the field outside the resonator is exponentially growing up as you go away from the resonator. And what I would like to emphasize here is that this is physical. It's not unphysical at all. And it is a consequence of the exponential decay of the mode in time. Let me illustrate that with this field. I mean, if you are far away from the resonator, it means that you are in the far field. So you have a leakage, and the leakage is basically proportional to 1 over r. R is the distance, exponential I omega t minus r over c. You have to choose the imaginary part of omega so that there is an exponential decay in time. It's obligatory. It's, if I could say, causality. And then because of this minus sign that you cannot change, this directly implies that the field is exponentially growing up as you go away from the resonator. The point is that this exponential growth has led to a debate in the literature over the past 10 years. And this debate can give the impression that there is a strong issue there, that it is not solved and that it is complicated. I just would like to say no. I mean, actually, the normalization of a quasi-normal mode is something which is straightforward and which has been performed for any kind of resonator since now almost 10 years. Recently, to emphasize this point and to remove any misleading discussion, we wrote a review article in Optics Express on the normalization, orthogonality, and completeness of quasi-normal mode. And if you look to section 4, you will see that we compare the 4 main approaches that have been used in the literature during the last decade. With respect to their exactness, some of the methods are wrong, simply wrong, mathematically false. To their domain of validity, you have some method which not allow you to normalize the quasi-normal mode in the general case, and also from their numerical implementation. And if you read that, you will see that normalization of quasi-normal mode is no longer an issue. Now, back to man. The normalization method used in QNM Hague and QNM Pole are completely different. And if you read the section 4, you will see this following conclusion, that the two methods are first completely mathematically equivalent. The two methods have a general scope, and in fact are the only one available so far for normalizing arbitrary geometries. And both methods are easy to implement, and they provide, once implemented, quasi-identical normalized field. We report for relative errors which are typically of the order of 0.04%, which is within the numerical accuracy. Let's move on now to a presentation of the toolboxes. And let me start by the reconstruction toolbox, which is in the version V8 of MAN, which is the new toolbox, which is, I think, very interesting. This toolbox comprises both frequency and temporal domain reconstruction. And in fact, in the frequency domain reconstruction, it is composed of two toolboxes, which are the alpha coefficient toolbox and the reconstruction toolbox. What does it mean, reconstruction, in quasi-normal mode theory? It means that the total field here is going to be written as a sum of the incident field plus the scattered field. And the scattered field is going to be written as a summation over the quasi-normal mode of the resonator, weighted by some excitation coefficient alpha m, which are known analytically. So once the mode here are computed and are known, then the reconstruction is fully analytical. And the expected benefit of that is that you can have a straightforward interpretation because you can directly read the scattered field as a sum of contributions of the natural resonance modes of your system. And in some cases, not always, but in some cases, important cases, you can have a superior numerical efficiency compared to standard method like the FDTD, for instance. Let me start by an example in the temporal domain. I would say this example is quite similar to the Helmholtz acoustic resonators that I showed at the beginning. Here what we look at is what is called a dolmen, which is composed of 3 metallic nanoparticles. And then we send a pulse onto this dolmen, and we record at the position in space the field which is scattered by the dolmen. And here, the blue curve that you see here is coming from an FDTD calculation, because often in the temporal domain, this is a software which is preferred by people. And obviously what you see is that you have a beating here. So it means that probably several modes are excited. But the FDTD doesn't tell you which mode are excited. If you use this quasi-normal mode expansion in the temporal domain in that cases, what you can do first is to compute the most important quasi-normal mode, in the frequency range of the pulse. Here is a visible frequency range. And then, once you know this mode, by performing an overlap integral with the incident pulse, you can compute analytically the excitation coefficient of each mode, which are called here beta, because they are in the temporal domain. And when you make the sum of the contribution, then you get the field at the position A. Of course, the prediction cannot be perfectly exact because you just consider 3 quasi-normal modes to reconstruct the field. You don't consider all the quasi-normal modes of the system. And here what I show is the comparison between the FDTD data and the modal expansion with only 3 quasi-normal modes. I would say there are many things to say, but rapidly, you see that at the beginning here, there is quite a, I don't know if it is significant difference, but there is a difference at least, which is visible. And the mistake which is done here is done by the modal expansion, because we neglect all the high frequency quasi-normal mode of the system. So it means the initial transient regime cannot be computed exactly. But then you see that after a while, especially in that range, you have a pretty nice matching between the FDTD result and the modal expansion, which means that basically the system can be described by only 3 modes in that regime. And then if you go a little bit further away here, you see that there is a dephasing between the 2 calculations. But in that case, the mistake comes from the FDTD. With the finite element method that we used, we have a perfect or nearly perfect or very good discretization. And here what's happened is that you have dispersion in the FDTD result. I have to say, to summarize this, and I think you will really understand, what happened in that system is that with a few modes only, you cannot be perfect. But if you compare to the FDTD, you have a lot of advantages here. Because here, what you have is, you have a physical description of the system. You know which mode is excited. You know with what coefficient it is excited. At the same time, if you think in terms of making several computations, because imagine I want to change the pulse width, or the angle of incidence, or the polarization of this pulse. With the FDTD approach, I have to recompute all. I cannot save one addition of the previous calculation. In that case, with quasi-normal modes, the quasi-normal modes are already computed. And then since the beta coefficients are analytical, you will get the result very rapidly. Let me move on now to a reconstruction in the frequency domain. It's a case of a bow tie antenna here, and what we are going to compute is the extinction cross-section. So first what we did is we used COMSOL, and for each frequency here, we computed the extinction cross-section, and that's the blue marks. So that's basically, I would say, the exact COMSOL data computed in the frequency domain. Alternatively, what we can do is that we can use QNMA in that case, and we are going to compute many quasi-normal modes of the system. In fact, when we make this computation, we use perfectly matched layer, and I would say that the quasi-normal mode, the real modes of the system, they are here in the complex frequency plane. And all the other points here, and we computed many, maybe 1,000 in that case, they are, I would say, PML modes or numerical modes, but they are there because the basis is going to be complete if I use them. And then we can start the reconstruction. First, we can take the fundamental quasi-normal mode. You see, it's this point here. Then we can simply write that the field is equal to alpha 1 E1, which is not exact, of course, but we can just reconstruct with one quasi-normal mode. And then once we assume that the field is given by alpha 1 E1, we can compute the extinction cross-section, and what we find is a red curve. Then we can take 4 modes to enhance the accuracy. And in that case, this is a result that you can obtain by assuming that the field is now alpha 1 E1 plus alpha 2 E2, etc. And pay attention, because the result is already quite accurate. You don't have all the resonances, but the mistake that you do here is not very large because you are in I would say, in log scale. Then you can 10 modes. And I would say that basically with 10 modes, you get the response with high accuracy. Now we have a movie showing that we are going to take more and more modes. You see now we take the numerical modes, and as we take the numerical modes, the accuracy of the reconstruction is better and better. Here you have computed the mean average value over the full spectrum that you can see here. So that means this is a mistake that you do, average over several decades from 0.2 here to 0.7, if I could say. That's quite large. Another example about this completeness, I insist on that, right? Because you will see the literature is not always accurate on this point, but I would like to be extremely accurate. Once you include the numerical modes, it's complete. Here is a case much more difficult than the bow tie, because you have, let's say, a nano antenna here, which is onto a slab waveguide. So that means that not only the quasi-normal mode leaks into free space, but they also leaks into the guided mode of the slab antenna. It's a much more complicated system. Here is a reconstruction, right, of the extinction, again, as a function of the frequency. Get a look, we have a quite large interval. So we compare COMSOL data in red, basically, with a reconstruction with only the quasi-normal mode, and the quasi-normal mode plus the PML modes. And here you have a look to the convergence, and you can see that when we include something like 10 to the 3, it's quite a significant number, but at least what we show is that even for this very complicated case, the extinction, I mean, the error which is made is very, very small, 10 to the minus 5 in that case. I would say this article contains state of the art, even 3 or 4 years after, on the reconstruction, with quasi-normal modes, PML, and numerical modes. The PML modes or the numerical modes, they are convenient because they make the basis complete. However, there is an inconvenience with them, that we need to compute many of them to have a high accuracy. And to remove this limitation, what we have done, we have proposed a method which is different, that we have implemented into the interpolation toolbox, that allow you to keep the physics with the dominant quasi-normal mode of your system, but allow you to compute rapidly the contribution of all those PML modes without computing them. Let me look to a general response of the system, of any system as a function of the frequency. What you have in general is you have a smooth background here, which is probably due to the excitation of high order quasi-normal mode, or even quasi-normal mode with a very low frequency. And on top of that, you have a superposition of peaks, which are due to resonance, which are the physics which is of interest for your system. And in the hybrid method, what we do is that basically we compute the resonance with quasi-normal modes. So that means we keep the physics in, and we compute the smooth background contribution with real frequency simulations. And by doing that, we combine physics and efficiency. Let me illustrate the principle of the hybrid method on the case of a silicon nanodisk on a metal film. First, what we do is that we compute the quasi-normal mode in the spectral range of interest. And what we found is with QNM egg, in that case, we found that we have 6 quasi-normal modes. From this computation, we first compute analytically, because the alpha coefficients are known analytically for the driving field, which is a plane wave that we consider. We compute this sum over 6 terms. And what we have here is a field. We reconstruct the field, in fact, with only 6 quasi-normal modes. And this is the field. What we plot here in blue is this reconstruction at one point in space, probably in the nano gap here, as a function of the wavelengths. Then, in a second step, what we do, we compute the solution for, in that case, 8 values selected in the spectral range, which are called exact data. In that case, we use COMSOL. We solve the issue 8 times at 8 different frequencies. From that, we compute the difference here between the points and the blue curve. And we obtain the 8 circle in that case. And from this 8 circle, the key idea here of the work is that it is a background. So this background should vary gently with the frequency. So that means I can, from the 8 point, or only from a few points in general, I should be able to interpolate with a high accuracy. That's the important point. And then by interpolating, I found the background. Then when I have the background and the contribution in blue, I make the sum of the blue curve and the violet curve, and I get the results. Here what I show is just a comparison. And of course, what you could imagine is that the comparison is excellent over the full spectral range with only 8 computation at 8 real frequency point plus 6 computation at complex frequency. We get a value which is below 10 to the minus 2. In the previous slide, I show you a reconstruction in one point in space. In fact, you reconstruct the field everywhere in space at the same time. Here is the field that is computed in the central part of the dielectric gap here. This is a reference value obtained with COMSOL. So we are at a given frequency now. I mean, I cannot plot all at the same time. This is a reconstruction with 6 QNM, so there is a difference. When you introduce 7 frequency domain points calculation, there is still some difference, but with 20 n equal to 20, we have an excellent match. Got to look how the relative error is decreasing very fast. Let's move on to a rapid presentation of the grating toolbox. In MAN, in fact, we provide 2 kinds of computation. One for plasmonic crystal, where we compute the dispersion diagram. And in that case, we compute the complex frequency as a function of real value of the K wave vector, if I could say. And we have also a grating toolbox here where we compute the complex frequency not for a fixed value of K, but for a fixed value of theta. And that's very important. That's the main lesson of this work. I mean, when you are an experimentalist, what you do is you fix theta, and then you scan over the wavelengths to record, let's say, the transmission, the reflection, whatever you want. But you don't fix K. So the resonance of your grating are not a resonance as a function of omega as a function of K, but as a function of omega of theta. Here I show the numerical example that we provide in the toolbox. It's a lamellar grating, a one-dimensional one, which is composed of grooves etched into silver film. We use the TM polarization, which is the more complex one, and we have an angle of incidence of 30 degrees. I show on the top of the slide the 7 dominant modes that are excited in the visible spectral range. Importantly, and I insist on that, the mode are computed for a fixed value of theta, not of the parallel wave vector, and that's quite unique in the literature. What you see on the bottom is the reconstruction that we perform with 7 quasi-normal modes. It is a blue curve, actually. And then at that time, we were not able to implement the interpolation toolbox, so we computed many PML modes. But if we do the job now, we will use certainly the interpolation toolbox to be more efficient, and then we can reconstruct the field with the quasi-normal mode plus the PML modes or the numerical mode, and this is a red curve, and here you have a comparison with the rigorous coupled wave analysis data, which is very well matching. Let me now introduce the Purcell factor toolbox, which is in fact incorporated in the frequency domain reconstruction toolbox. This is not a toolbox by itself, if I could say. Everyone knows what is a Purcell factor is, but let me introduce it a little bit differently. I mean, let me first consider this case of a micropillar where you have a quantum dot inside. Of course, you will like to know what is the decay rate of the quantum dot due to the excitation of the resonance mode of the micropillar. But you can have also some related important relation. For instance, you can ask yourself, what is a fraction of the emission that is coupled to the cavity mode? This is known in the literature as a beta factor. And now, if you consider the light emitted into the cavity mode, you can ask yourself if this light is emitted into the air clad above or on the boundary here. That's not easy to interpret. Also, you can consider this NPOM resonator composed of a silver nanocube on a metal film. And you can ask yourself what is a fraction of the mode emission, which, for instance, excites the surface plasmon mode. I would say that the toolbox that we have implemented could allow you to compute and even to understand all those quantities, which are not straightforward. The formula in red is the main result, if I could say, of the quasi-normal mode expansion of the Purcell factor. What you can see is that the modification of the total decay rate here of a quantum emitter which is placed in the near field, let's say, of a micro or nano resonator, can be as a sum over the quasi-normal mode. And you find the Purcell result here. It is Q over the real part of V. In non-Hermitian theory, you have to know that the mode volume is not a real quantity, but it is complex. So this is Q over the real part of 1 over V, multiplied by a Lorentzian term, which essentially tells you that the decay rate is large when the frequency of the emitter is matched with the frequency of the mode. And you have in this non-Hermitian theory, I mean, you have also a correction term that you see here. When the imaginary part of V is not equal to the real part of V, actually this term is significant, and you can see that the response can be different from a Lorentzian term. Also, it may happen in some situation when M of V is quite large, it may happen that this quantity could be negative. And this is what we illustrate here to show how precise this theory is. Where here we consider that it's a numerical calculation, 2 metallic nanorods, put an emitter into the gap, and what we did first was use COMSOL, and we computed the normalized decay rate. It means that we computed the normalized intensity of light which is emitted. And this is a circle points. So it's a frequency domain calculation, and each time here, for each frequency, we solve the problem. And then what we did is that we computed the quasi-normal mode in this spectral range. We found that there is 2 dominant quasi-normal modes. And here what I show is that once you have normalized this quasi-normal mode, you know at the position of the particle of the emitter, you know the mode volume. And you see that the mode volume here is a complex quantity. And you see also that the imaginary part is really large. In fact, is as large as the real part. And then from this mode volume value, you know the Q factor. We use QNM pole at that time for this computation because we just need to have two of them. Then we plug into this formula. We know the Q, we know the mode volume, and it's analytical. And then we get the blue and the green curve. And what you see, what is remarkable there, is that, of course, as I said before, none of the response is Lorentzian. But at the same time, you see that even the zero is there. So you have some response, even in the green at this frequency, but almost the blue here, the response is negative. So it means actually, and that's counterintuitive for those who are used with Hermitian theory, but not with non-Hermitian ones. It means that a mode can decelerate the spontaneous emission rate, in fact. And when we make the sum of the two, I mean, you get the red curve, which is a very nice agreement with the COMSOL calculation, if I could say. Now, if you look to that, I just to insist what the physics that you learn with the quasi-normal mode approach, that if the one, I mean, compute this, many people can do that using a real frequency solver, what they will say, oh, come on, there is a single resonance in that system. And basically, you excite this resonance, and the response is not Lorentzian because you have a Fano response because you couple with a continuum. And that's completely incorrect, this interpretation. And the good interpretation is that you have two resonances, of course. I will not go into the detail, but for those who are interested, with Massimo Gurrioli, we provided a very quantitative evidence experimentally that, in fact, you cannot use an Hermitian theory, even for a system with IQ, when you have two resonances like this, which spectrally overlap. What Massimo Gurrieli and his group has done, he has recorded the photoluminescence of a quantum dot, which is placed into one of the two cavities. And this is basically the circles here, the circle marks. This is experimental data. And what we did is that first we try a Hermitian theory. In Hermitian theory, it just tells you that each mode contributes positively with a Lorentzian. So what we try to do is to fit this experimental curve with a sum of two Lorentzian. And it doesn't work. I mean, even by assuming any kind of value for the parameters, the best fit that we could obtain is the blue curve. So you see that the deep here, we don't have it. So what we did next is we take this system, computed with the QNM pole solver, the two quasi-normal modes of this system, then computed the mode volume at the position of the quantum emitter, and then there is no fit at all, and then we plot the orange curve and the green curve and make a sum of the two and get a very nice agreement with the experimental data. Let me finish the presentation with multipolar expansion toolbox. Many of you probably know that when you have a resonator which is placed into uniform background, let's say in air or in a dielectric background, you can expand the scattered field as a sum over vector spherical wave harmonics. And this expansion, it's important to realize first that it is performed at each frequency here. So that means that in this graph, for instance, the scattering cross-section is expanded into this spherical wave harmonics for each frequency. So for instance, when you want to make a Kircher effect, right, you have to match the contribution of the electric at magnetic dipole, but when you will realize that, you will match it at a single frequency, which is the intersection of two curves here. What we have done is different in the spirit, and that's important to understand that. What we have been able to do is to attribute to each quasi-normal mode a spherical harmonic content. So that means that when we compute in the complex plane, for instance, the quasi-normal mode of a dolmen here, for each mode at a complex frequency, we are able to say this mode contribution is basically a magnetic dipole along Z and an electric dipole along X. So what we have tried to do in that case is by changing some parameter, you know, like the gap width here or the lengths and widths of this metallic nanorod here, we have been able to try to manage to fabricate what is called the Janus resonance, which means that for this mode, this mode 1 here, we try to design it so that the px is equal to plus minus I multiplied by mz. And at the same time, what we try to do is to push away in the complex plane, to push away all the other modes. So that in the complex plane, what we try to have is a mode which is isolated, which means that if I shine it at the resonance frequency of this mode or around, I will excite dominantly that mode. And we have tried to manage that this mode has a content, a spherical harmonic content which is fixed. And as you can see here, by changing these two parameters, basically we move into the complex plane, and for this mode we succeeded. I mean first we move the gap here, and after that we reduce the lengths and the widths, and then at this point here, in fact, we have this quantity which is matched in that case. And at the same time, you see that mode 2 has been pushed away. And also, get a look, the mode 3 has been pushed away because now the imaginary part of that mode is much smaller than the imaginary part of this one. So also they have similar real frequency. They will not be excited with the same efficiency. And this is a kind of result. I will go rapidly. That's for, let's say, a coupling of a dolman. So you can investigate two situations where you rotate the dolman, as you can see here. And you see that in one case, because of this Janus effect, we couple light efficiently into a waveguide, or in the other case, we don't couple light. And the important point here of the result of this design in the complex plane is that you see that the ratio between the coupling, I mean, basically we have the resonance. So the ratio is excellent over a broad spectral range. We not just realize a matching for a single frequency, but we realize a matching for many frequencies around the resonance of this Janus mode that we excited. Also, as a function of theta, right, we are also quite tolerant. Let me finish by the acknowledgements. It's always a pleasure to have many colleagues to acknowledge at the end of a presentation. I would like especially to acknowledge Wei Yan, who was a postdoc in my group in Bordeaux a few years ago and is now in Westlake in China. He has been involved quite significantly in the elaboration of the eigen solver QNM Hague. Also a big acknowledgement to Tong Wu, who is now postdoc in my group. I think that the software exists mainly because of him. And if you have a technical question to address, please do not hesitate to contact him at this email address. I would like also to acknowledge former collaborators like Christophe Sauvant and Jean-Paul Hugonin when I was in Paris. At the beginning of the project, I mean, they have a significant contribution in terms of ideas. Also, I would like to thank Jiangji Yang, who is now in Meta in California, who significantly helped into the establishment of the quasi-normal mode story in Bordeaux when we arrived in 2014-2015. Thank you for your attention.